This video will be more of a follow along. I would recommend that you pause the video when the problem is on the screen, try the problem yourself, and then come back here to see how I solved it. There's multiple ways you can solve these, so maybe your solution is fine, but if you got stuck, hopefully my thought process and explaining my thought process can help. And some of it might just be algebra that you maybe got stuck on. So hopefully my worked out solution can be of help as well. Okay, so we're going to be doing about 13 problems on testing infinite series for convergence. This is a very standard type of problem you can expect on your chapter test or even on the AP exam. This will for sure be covered. All right, so let's go to the first problem right away. Number one, we have this series summation as n goes from 0 to infinity, 2 over 7 to the n power. So does this series converge or does this diverge? So go ahead and try this yourself first. Pause the video if as needed. Okay. By the way, I took these problems from a AP practice, AP test prep book, a very old one. So if you have a hold of this, it's the same problem set. Okay. Problem number one, this is how I solved it. I recognize that this guy is just a geometric series. It's some common ratio to the n power. Okay. We know when geometric series converges, that's when the common ratio is less than 1. The absolute value of the common ratio is less than 1. What's the common ratio here? It's 2 over 7. 2 over 7 is less than 1, so the series converges. We even find the sum, actually, even though this problem didn't ask for it, we can find that the sum is 7/5. Okay. Number two, does this series converge or does this diverge? Summation as n goes from 1 to infinity, 4 over n cubed. Okay, hopefully you tried it yourself. This one's hopefully pretty simple. We can rewrite the series as 4 times summation. I didn't write the limits, but summation of 1 over n cubed. This is a p series with p equals 3. We know when p series converge, that's when p is greater than 1. The p value here is 3. Therefore, the series converges. As simple as that. Pretty easy. You could, of course, have done a comparison test and stuff like that as well. That's totally fine as well. I think this is the easiest way. You just recognize the p series. Right. Number three, summation as n goes from 1 to infinity, n squared over 5 to the n. Does this converge? Does this diverge? Which test did you pick? Hopefully you picked the ratio test. The big clue is an exponential. The ratio test is good for exponentials and factorials. By the way, if you don't know which test to use or are struggling with that, I have a video explaining my thought process on that. I can link it. Maybe you should watch that first and then come back to here if you're struggling. Okay, but in that video, I did explain that precisely that the ratio test is really good for exponentials and factorials because when you do the ratio test, things would cancel nicely. So we go through the motions of the ratio test. Limit as n goes to infinity, a sub n plus 1 divided by a sub n. So this is a sub n plus 1 over here. Or if it's n, replace it with n plus 1. And multiply by the reciprocal, which is the same thing as dividing by a sub n. Okay? This is the algebra, 5 to the n divided by 5 to the n plus 1. Properties of exponents, you can subtract the powers. So n minus parentheses n plus 1. That becomes 5 to the negative 1 power. So it's just 5 on the bottom. Oh, over here, I even combined the terms, like terms, okay? And then these, you can't really simplify, so I expanded it out, okay? The 1/5 is a constant, I could pull it out in front. And now we take the limit of this guy. What we can do the shortcut way, this is a rational function. Degree test. The degrees are the same. Take the ratio of the lead, or the biggest degrees are the same. So we take the ratio of the leading coefficients, which is 1, and that's the limit. So the limit is 1/5 times 1, which is 1/5. The ratio test says this limit has to be less than 1 for the series to absolutely converge. And 1/5 is less than 1, so the series converges. If it absolutely converges, it converges. Okay. Number 4, what about this guy? Summation as n goes from 1 to infinity, 1 over cube root of n to the 5th plus 5. Okay, hopefully you tried it yourself first. This is what I did. I compared it with a P series. I compared it with something very similar. Whenever you do a comparison test, you probably want to compare with something very, very similar to make your life easy. So I compared with 1 over cube root of n to the fifth, which I can write in exponential form. 1 over n to the 5 third power. This is the P series. Okay. We know that cube root of n to the fifth plus 5 is greater than or equal to cube root of n to the fifth because it's bigger. We're going to be cube rooting something bigger, so it's going to be bigger. Okay. Therefore, when we put it on the bottom of a fraction, this guy will be smaller than this guy. Okay. We're dividing by something bigger, so the final value will be smaller. Okay. Now, as I was hinting earlier, this guy that we're trying to compare to is a P series with P equals 5/3. We know a P series converges if P is greater than 1. Therefore, this guy would converge. And therefore, because our guy is even smaller than the thing we compared to, and we know the thing that we compared to converges, something smaller must also converge as well by comparison. Okay, that's how I approach this one by comparison test, direct comparison test, sometimes we call it. Number 5, summation as n goes from 1 to infinity, n to the n over n factorial. Which test do we use for this? If you got the hint earlier, we probably should use the ratio test here. There's a factorial, and there's also an exponential. Okay, so we go through the motion. Limit as n goes to infinity, a sub n plus 1 divided by a sub n. You got to be careful with your parentheses and all that here. Okay. So I grouped the like terms together-ish again. Did I do that? Or what did I do here? Even I don't remember what I did. So let's figure this out. Okay. So this is the first step, a sub n plus 1 divided by a sub n. Okay. What's n plus 1 factorial? That's n plus 1 times n minus 1 times n minus 2, so on and so forth. Okay, so we can rewrite it as n plus 1 times n factorial. Okay, we just got the first term, we separated out the first term, and then everything else is the same, n factorial. Okay, we want to do that because this will cancel nicely, these two n factorials, okay? And now, yeah, that's what I did here. So what else can we do to simplify? Well, n to the n plus 1 to n plus 1 power divided by n plus 1, we can use properties of exponents to subtract the powers. N plus 1 minus 1. So that's just to the n power. Okay? And now, here we can use another property to rewrite this as n plus 1 over n to the n power. Okay? Now what do we do from here? Hopefully this looks familiar. If we divide through by the n is 1 plus 1 over n to the n power. Now does this look more familiar? It's e, the limit definition of e. Okay, so when we take the limit, it's e. Okay, so basically you had to be good with your algebra here. And you had to be able to recognize this limit was e. Okay? If you were not able to see that, you might have gotten stuck. So hopefully this could be of help if you did get stuck. Okay? Now, what does the ratio test say? If L is greater than 1, the series diverges. What's the value of E? The 2.7 something, right? That's clearly greater than 1, so the series diverges. Okay? And if you had some intuition in the beginning, actually, exponentials grow much faster than factorials. So that's why it diverges. If you actually took the limit of this guy and did a test for divergence, it's probably not equal to 0. Okay. Number 6, this is a little different representation. Instead of a closed form summation notation, they gave us a list of numbers here, plus a dot, dot, dot. So how do we determine the convergence of this? So maybe, as I hinted, you would want to rewrite this as into a summation notation first, which is simple enough. It's summation as n goes from 1 to infinity, 1 over n to the n plus 4, sorry. Or we can simply just rewrite it as summation as n goes from 5 to infinity, 1 over n. This hopefully looks very familiar. It's the harmonic series, right? Or a p series, p equals 1. with this representation, since we know the harmonic series diverges, this series must diverge as well. It is the harmonic series. It just starts from n equals 5 instead of n equals 1. I should say that. Okay. This is similar. Does this guy converge or diverge? So again, maybe let's write it in a closed form summation notation first. We realize that each term is being multiplied by 1/4, it looks like. Okay? So that means it's a geometric series, right? With a common ratio of 1/4. Actually, we don't even need to write it in the summation notation. We just realize that this is a geometric series with r equals 1/4. And we know that the geometric series converges if r, absolute value of r, is less than 1. 1/4 is clearly less than 1. So our series converges. It's a geometric series. Okay. Number 8. How about this guy? The summation as n goes from 1 to infinity, 5n squared minus 6n plus 3 over n cubed minus 7n plus 8. How do we determine the convergence of this guy or not? So if you watched my crash course, not crash course, that video on testing series and deciding which test to use, this looks like a rational function. So when it looks like a rational function, the test to probably use, the easiest test in my opinion to use, is the limit comparison test. Okay? Now what did we compare to? We compare what the strategy is, pick the biggest degree on top, pick the biggest degree on the bottom. We don't really care about the coefficients. We could pick 5n squared over n cubed, or we could just pick n squared over n cubed, which simplifies down to 1 over n. Okay? Now we do the limit comparison test. Limit as n goes to infinity of the original guy divided by the guy you want to compare with. So divide by 1 over n, this is the same thing as multiplying by n. Okay? And we distribute this n to each of the terms. Now we take the limit. The degrees are the same. So we take the ratio of the leading coefficients. So it's 5. Okay? So what does the limit comparison test say? If this limit is finite and positive, okay, so greater than 0, less than infinity, okay, either both series converge or both series diverge. So this guy is the harmonic series. It diverges. Therefore, our guy also diverges by the limit comparison test. Okay? That's how I would approach this one. Number 9, summation as n goes from 1 to infinity, cosine of n pi divided by square root of n. Does this converge? Does this diverge? How do we approach this one? Are we going to let that cosine of n pi intimidate us? We will not, because we realize that n is just an integer value. 1, 2, 3, 4, so on and so forth. So what's cosine of 1 times pi? Cosine of pi? That is -1. What's cosine of 2 pi? That's 1. What's cosine of 3 pi? -1. Cosine of 4 pi? 1. So on and so forth. So we can rewrite this cosine of n pi as -1 to the n. No need to be intimidated anymore. Okay, now how do we determine the convergence of this guy? I dropped the limits, my bad, but how do we determine convergence of this guy? We can use the alternating series test, can we not? We know that 1 over square root of n is a decreasing sequence. I didn't show it here. At the very least, you need to state it. Okay, to prove it, you need to take the derivative. That's the easiest way to show that it's a decreasing sequence. If the derivative is negative from some point onward to infinity, it's a decreasing sequence. But at the bare minimum, you should state it. Okay? And we take the limit as n goes to infinity of 1 over square root, and that's 0. So by the alternating series test, our series converges. So the trick here, trick per se, is rewrite this cosine of n pi as -1 to n. Okay, we realize that it's just an alternating sign for integer values of n. How about this one? Summation as n goes from 1 to infinity, 3 to the n plus 4 over 2 to the n. Okay, so I did this in 2 different ways. Method 1, we can just do a comparison test. It looks very close to 3 over n over 2 over n, which is 3 over 2 to the n power. Okay, so maybe let's compare with this guy. We notice that our guy is greater than 3 to the n over 2 to the n. Okay, within this interval at least. Okay. We know this guy diverges since it's a geometric series with r equals 3 halves. 3 halves is bigger than 1, so that's why it diverges. Okay. Since our guy is even bigger than something that diverges, our guy is going to diverge as well. So here's one way to determine that this diverges. Another way is just to rewrite the series a little bit. We can break it up into 3 to the n over 2 to the n plus 4 over 2 to the n. We split the fraction, and then by properties, we can break up the series as well. Okay, this guy diverges, again, precisely because it's a geometric series with r is equal to 3 halves, which is greater than 1. Doesn't matter that this guy converges. It does converge, but this guy diverges. This piece diverges. So something infinite plus something finite is still going to be infinite. So that's why this guy diverges if we do it this way as well. Okay. I think we have 13 problems in number 11. We're almost done. How about this guy? Summation as n goes from 1 to infinity, 8n cubed minus 6n to the 5th over 12n to the 4th plus 9n to the 5th. This one's actually pretty simple if you are able to realize that we can just use the test for divergence, or some books call it the nth term something. I don't know the name. I learned it as the test for divergence. If we take the limit as n goes to infinity of this guy, it's minus 6 over 9, which is not equal to 0. Remember, for an infinite series, for a chance for an infinite series to converge, the limit of the sequence inside has to be 0. It needs to be 0 for a chance for the series to even converge. If it's not equal to 0, imagine you're adding an infinite number of minus 6 over 9. It's going to grow to negative infinity, basically. Okay? So that's why the bare minimum for a series to possibly converge is that the limit of the sequence has to be 0. And it's not in this case, so the series diverges. You could have probably did a comparison test as well, but I was able to see this right away. Usually, if you can use the test for divergence, it's the simplest way to determine divergence, usually. Number 12. Summation as n goes from 1 to infinity, square root of 3n plus 1 over n to the 5th plus 2. How do we approach this one? Okay. Let's go down our list. Let's pretend we're seeing this on the test, a test. I don't know if you're taking AP Calc or not, or you're taking calculus at some other school. But let's pretend we're on a test. What are the tests we know? Can we use the test for divergence here? If we take the limit as n goes to infinity of the sequence, it's 0, so it doesn't help us. Can we do the integral test? I don't want to evaluate this integral. It seems quite difficult. So let's not try that. Maybe we have to at the end if we exhaust all our options, but let's avoid that for now. It's not an alternating series, so we can't use the alternating series test. Can we use the ratio test? It might be doable, but it seems kind of hard. Remember, the ratio test is good for factorials and exponentials. I don't see that here. So maybe not that. I don't know if in AP Calc BC you learned the root test, but is the whole series to n power? It's not, so not the root test. So what options do we have left? We either do a comparison test, a limit comparison test, or maybe the integral test. So maybe let's try to use a comparison. Usually when I see a series that I don't know right away which test to use, I go through this thought process. The last resort is always, for me, the integral test. And the second to last resort is the comparison test, because sometimes it's hard to determine what to compare to. Okay. So here I decide to use the comparison test, or limit comparison test, I guess I used. Okay. Whenever you do either the comparison and limit comparison test, as you noticed, hopefully so far, you want to usually pick something very close to our guy, right here. Very similar, but simpler to determine the convergence of. Okay, so what did I do? I picked the biggest degree on top, which is n. biggest degree on bottom, which is n to the fifth, and I kept that all to the half power. Okay. Now I can use properties of exponents, so it becomes n to the half over n to the 5 halves. This simplifies down to 1 over n squared. Okay. Now I did a limit comparison test. So here you have to be good with the algebra here in order to do this successfully, like I did over here. Limit as n goes to infinity of this guy divided by this guy. Okay, so divided by 1 over n squared is the same thing as multiplying by n squared. Okay, now how do we evaluate this limit? Well, we could probably use L'Hopital's rule, but it'll get very messy. So I did not choose to do that. Instead, I decided to bring this n squared inside square root. So it becomes n to the fourth. Okay, so imagine square rooting n to the fourth, you get back n squared, right? And it's only the positive because n is approaching infinity. Okay, so here, remember how do we take the limits of these guys without L'Hopital's rule? You factor out the biggest degree. So in the top, I factored out another factor of n, so it became this. And the bottom, I factor out n to the fifth. Okay, now properties of radicals or exponents, same thing. I rewrote it like this. So these would cancel to 1, right? And now we can take the limit of what's left. Okay, as n goes to infinity, 1 over n goes to 0, and 2 over n to the fifth also goes to 0. And remember, we just said this cancels to 1. So we are left with limit as n goes to infinity of square root of 3, which is just square root of 3. It's a constant, right? Okay. Now, what does the limit comparison test say? If it's finite and positive, this limit, then both series converge or both series diverge. This guy's a p series with p equals 2. We know it converges. So therefore, our guy also converges. So the hard part for this one, in my opinion, is picking the series to compare to. And then the next hard part was the algebra. Okay. You could probably pick another different series to compare with. If you did, great. Maybe leave it in the comments so that other people can try it as well. So this is one possible solution. Okay, last one, number 13. Does this series converge absolutely, converge conditionally, or diverge? Let's go ahead and try this one. So we got to recall what the definitions are first of absolute convergence, conditional convergence. Something's absolutely convergent if the absolute valued version of the series converges. Okay. It's conditionally convergent if the absolute valued version diverges, but the original guy converges. We call that conditionally convergence. Okay. And I didn't write it here, but it's implied that if both diverge, then it's neither, right? It diverges. Okay. So we probably want to find out if the absolute valued version converges or not first, because if it converges, then it's absolutely convergence right away. Okay. And remember, if this guy converges, the absolute value converges, then this guy also converges. Just by the definition of absolute convergence, okay? But the implication is absolute convergence. Okay, but anyway, so I was saying, let's first check the absolute value version, if it converges or not. Okay, so how do we determine the convergence of this guy? Well, we can do a limit comparison test with cube root, not cube root, fifth root of n on the bottom. This is a p series of p equals 1/5, right? So we go through the motions of the limit comparison test. I will skip through the algebra this time. You can definitely pause the video to check it out. The limit will be 1 over fifth root of 3. And the limit comparison test says that if this limit is finite and positive, which it is, both series diverge or both series converge. This guy, the one we compared to, diverges. I think I said it earlier. It's a p series of p equals 1/5, which is less than 1. So it diverges. Therefore, our guy, this guy, the absolute value version, diverges as well. Since it diverges, it's definitely not absolutely convergent. Okay. Now, we have to check if it's conditionally convergent, though. Because even though this absolute valued version diverged, maybe the original, with the alternating sign, converges, and we call that conditional convergence. So we got to check. All right. Now, how do we determine if this guy converges or not? We can use the alternating series test. The sky without the alternating sign is a decreasing sequence. Again, we can take the derivative and prove that it's negative to show that it's decreasing, but I didn't show that here. At the bare minimum, as I've said, you should at least state it because it's a condition to use the alternating series test. And if we take the limit as n goes to infinity of this guy, it's 0. So by the alternating series test, this guy converges. Therefore, since the absolute valued version diverged, but this non-absolute valued version converges, it's conditionally convergence. Okay? And that's it for this problem set. Hopefully this was good practice for you if you followed along. If you have further questions on any of these, feel free to leave it in the comments. If you solved it in any of them in a different way, feel free to also leave it in the comments so that other people can learn from how you did it as well. These are just sample solutions. So there's definitely multiple ways that you can approach these. All right. Please give this video a like if you found it helpful. And also please subscribe to the channel as well if you want to see more videos like this. Hopefully see you in another video as well. Bye.